Good evening, everyone. I hope you can hear me. Can you please confirm in the chat? Okay, that's great. Hmm. So it's 7:05. We can start. Let me share my screen. Okay. Okay, so we can start. For anyone new here, my name is Buruj. I'm a fourth year PhD student at IIT Delhi. I research graph machine learning. This is week 5 of our course on data analytics with Python. The purpose of these practice sessions is to apply whatever you have learned in code by real life examples. The way we do them is that I present you with the problem and I give you, let's say, 5 to 10 minutes to solve the problem. And after that, I provide you the solution. In case anyone has a doubt, then we go over the solutions. And mm, when we discuss these solutions, you don't have to take any screenshot or etc. because the code that we discuss in class is available on this GitHub repository. You would notice that this folder notebooks contains the previous week content, and this YouTube channel, wait, this playlist here, it contains the recordings that we're having right now. Okay, so I'll share these links with you later on. So this week we are covering, I believe, 2 sample tests. So let us start with that. Let me give you a question. The idea here is that you first have to identify which scenario it falls in. That is, which particular test should I apply? If you identify that, then you can do it using a library. Once you do it with a library, see if you can do it manually as well. Okay, so let me paste it here. I hope you can see my screen. Can you? Is the screen visible? Is the font okay? Can you read it? Okay, thanks. Let me start with this. All right. So the first question says, an article in the Journal of Environmental Engineering compares two instruments for measuring airborne particle concentration. Data for two instruments, device A and device B, when used at 10 specific monitoring sites on the same day, are shown in the table below, this particular data. We wish to determine whether there is any difference on average between the readings from these two devices. Using an alpha of 0.05, can you find any evidence to suggest that there is a significant difference between A and B? Okay, so this is the data that you have. If you require the data rather than copying, I can paste it in the chat for you. You can okay, so you can decide which category it falls into, and based on that, you can apply the test that you want. So it is 7:09. You can take maybe 7 to 8 more minutes, and then we'll see. All right, it's 7:15, so we can start. The idea here is that the data comes from the same distribution twice. They are just two different devices measuring the same thing. So your scenario here is of the difference between means, that is what we are computing, of dependent paired samples. You would notice that for the same site, for the same day, you have two calculations, device A and device B, device A and device B calculating the same quantity. So this is the test that you want to do. And how do you do a hypothesis test for this thing? You go for a relative t-test. So first we import the standard libraries that we always work with. The next step would be to create a data frame out of this. So we can say pd dot data frame, and we can just pass the data. If you notice this, we have a data frame, but to compute the to do the relative t-test, we actually need the difference between device A and device B. So we need an additional column. So we can say our delta column here is df dot device A minus df dot device B. This would be our difference. And if we print this, so now we have an extra column named delta. So how do you compute the t-test, t-statistic and the p-value? You use starts dot t-test relative. Okay, so this returns your t-statistic and a p-value. So what does this function take? It takes, I think it doesn't show any help. So scipy starts t-test relative. Yeah, so you just have to supply your two data frames, df1 and df2, and that will give you essentially this thing. You don't need the difference column unless you're doing it manually. So if you pass these two, you can say df dot, or you can also use it like this. You can say device A, and you say df device B, you close it down, and then you can say the decision should be reject if my p-value is less than alpha. We can define alpha here. Alpha was 0.05. Else, you say we fail to reject our null hypotheses. Based on that, we can print that our test statistic, that is our t-test in this case, came out to be this much. The p-value was this much, and decision at alpha equal to alpha was to okay. So we see that our t-test statistic is 13.6. Our p-value is essentially 0, but if we print the exact value, it's a very small number, like 2.3 e to the power of -7, and which is much smaller compared to 0.05. Based on that, we can compare that there is a significant difference between the calculations between device A and device B. So now that you know how to do it using a library, can you repeat this thing manually? That is, you manually compute the relativity test. Can you take 5 more minutes? You can refer to your lectures to do this part manually. So the key part here is this thing, dependent paired samples. Yeah, Siddharth, I hope the question is visible. Yeah, so for your ease, you can maybe follow this thing to compute it manually. All right, I think we can start. So what do we have? We already know that our alpha is 5%. We know that our sample size is the length of the DF. Okay. If we want to follow this formula, you would notice that we need this particular thing called D bar. We need the standard deviation divided by root of n, which is essentially your standard error to compute the t statistics. So how do we do that? We can say that mean of the differences, which is our d bar, is equal to tf delta. We already computed this difference column. We can just take its mean. We have to calculate the sample standard deviation because we don't have the population standard deviation. So we have s underscore d is equal to df delta dot std, and it is important to pass that the degree of freedom here in this case is 1, because this is not the population standard deviation, it's a sample standard deviation, so you have to compensate for that to correct it. Okay, once we have this standard deviation for the sample, we have to calculate the standard error. We can call it SED, and we can say it is just this divided by square root, or maybe we can even write it like this, r n raised to 0.5, that is root n. So this is our standard error. Given all this, we can calculate a test statistic, which is d bar minus a delta. A delta would essentially mean that is what does your null hypothesis think? That is what is the difference between the two means. Our null hypothesis says that the delta here is 0. So we can just subtract 0, or we can just leave it as is, d bar divided by the standard error, this thing. So we have our test statistics. We also know that our degree of freedom is sample size minus 1. Based on this, we have to calculate the p-value from the t-test. So how do you do that? We say that our p-value in this case will be, notice that we have to say whether there is any difference, greater or less. So it's a two-sided p-value. So we will do 1 minus the CDF that the t distribution gives us on the right hand side. So this is the absolute value of our t statistic, and we would like to take twice of this. That's the CDF and the absolute value t statistics, and we have to pass the degree of freedom as well in here. So DOF, this should give us the t value, and then again we can write decision like this. That is, if this, then this, and we can once again print this part. So we get the same thing. See, test statistic is 13.7944. Our p-value is identical, and the decision is that we have to reject the null hypothesis, and there is significant evidence that there is some difference between the two calculations. Any questions on this? Simple. All right. So let's mark this particular question as the difference between means. Let's go to another question and close this. Hmm. So the next question is this. A battery manufacturer is interested in increasing the average lifespan of rechargeable batteries. Two production processes are tested. Process 1 is the current method in use. Process 2 incorporates a new electrode that is expected to increase the battery life. Okay. From historical data, it is known that the standard deviation of the battery's lifespan is 15 hours, and this inherent variability is assumed to remain unchanged whether you use material A or material B. 12 batteries are produced using process 1, another 12 are produced using process 2. The 24 batteries are tested in random order. The two sample average lifespans are given like this and this. The first sample has an average lifespan of this many hours, the second one has this many hours. What conclusions can the manufacturer draw about the effectiveness of the new electrode? Does it have a larger battery lifespan? So you have to identify which hypothesis test you can use to answer the final question. You can once again take 7 to 10 minutes and then we'll proceed. Again, if you believe you can do it using a library, do that. Following that, it would be good if you could do it also manually to cement the idea. Okay, so while others are doing the current question, the previous question essentially says that you are calculating the same value on the same day. That is, you're at a particular site, you're using two devices to calculate the same entity. So this is a paired values. So device A and device B are a paired value for site 1, then you have for site 2 and site 3. You essentially have to answer if there is a difference between a significant difference between the means of the two things. Okay. So you conclude that this is a you have to essentially calculate the difference between means between dependent paired samples. In this case, you know that you have to do a peer t-test. Okay. So there is a way to do it using the library, but you also want to do it manually. So when we want to do it manually, from the lectures, you would know that this is how you do it. You first have to calculate the mean of your differences divided by the standard error of your differences, essentially. So you just do that. That is, your d bar is the mean of your differences, which is just delta of mean. Delta is just the difference a minus b. This gives you this column. You take its mean, it gives you the average of the differences. Then you have to divide by the standard error. For the standard error, you first need the standard deviation. In the standard deviation, you have to pass this degree of freedom because this is a sample standard deviation and not the population standard deviation. Once you have this, you just divide by square root of n. That gives you the standard error. And this thing divided by the standard error gives you the t statistic. The rest is the same that we have been doing for the last two lectures. That is, you compute the p-value. The p-value, you do it for a two-sided thing because um, you are saying that they are not equal. You're not saying it's greater or less than. So you have to cover both sides. So you essentially say, give me the t statistic for in either case, and then you just double the value to get the p-value. That p-value is much smaller compared to 0.05, so you can safely reject the null hypothesis. I hope it's clear. Yes, this lecture is recorded. Okay, so I believe we can start. The first and most important question is that this is a scenario of computing the difference of means once again. But in this case, you have independent samples. That is, there are two separate batteries you're getting samples from, and you know the standard deviations for both of them. Okay. It says that the lifespan is 15 hours, irrespective of the material. So you know the standard deviations. So given this information, you know that you have to compute a two sample z-test. Okay. So how do you do that? Let us first say what our null hypothesis is. We are saying that my mu1 minus mu2 is 0. That is essentially they are identical. My alternate hypothesis says that my mu2 is greater than mu1. It has a longer battery life. What do we know? We know that our alpha is 0.05. We know that our sample size is 12. It says here 12 batteries for both. We know that our standard deviation is sigma for both of them. Okay. You can also maybe add some comments. Known STD, sample size, and the delta based on our null hypothesis is 0. That is, there should not be any difference in the means if the null hypothesis is true. So we need our standard error for the sample. So how do you compute that? We can say standard error is np dot square root of what? First, you will have sigma squared divided by n. This is for the first battery. Then you will have sigma squared divided by n again for the second battery. So notice n, I'm using n because both of them have 12 batteries, 12 batteries, 12 batteries, and sigma is shared between the two of them. Okay, so this gives us our standard error. Based on this, we can get our z score. We can say that our z score is, did we compute the means? No, we did not. So we have this sample means x1 bar comma x2 bar is equal to 210 and 222. So we can say that this is my x2 bar minus x1 bar. This is the difference between the means. You subtract the delta from these, which is 0, but still, suppose we write this and we divide this whole thing by the standard error. So this is our z-score. From the z-score, we compute the p-value. In this case, it's a one-tailed p-value because we are only interested whether mu2 is greater than mu1. So we say that our p-value is 1 minus stats dot normal distribution, because this is a z-test. You take the CDF of this particular z-score. We have our p-value, and then we can reuse this part. That is, if we close this down, we can say that if our p-value is less than alpha, we can safely reject, otherwise we fail to reject. In this case, we have a z-score, we have p-value, we have an alpha, and we have a decision. So let's see what we get. We get a z statistic of 1 point this much. Our p-value is, in this case, we can even do it using this, our 0.02 compared to 0.05. Maybe we can even do this. Yeah, so this is less than this, so we can reject the null hypothesis. That is, it is safe to assume that is your second battery has a longer lifespan compared to battery one. This case is difference of means from independent samples when the standard deviation is no. So this is our second question. Let's go to the third question. We can close this part. So we have done this, we have done this. Let's do this one. Okay, so question number 3. A hospital is evaluating two different automated blood pressure monitors for its use in emergency department. Both devices are calibrated to produce the same average blood pressure reading. However, hospital admins are concerned about measurement consistency and would like to adopt the device with lower variability. Okay. A random sample of 18 patients is measured using device A, resulting in a standard deviation of this much. This standard deviation is for these 18 patients. It's a sample standard deviation. A separate random sample of 15 patients is measured using device B, resulting in this sample standard deviation. With 92% confidence of the ratio of these population variances, can you decide if one method is preferable over the other? So Tanu is asking about the exam questions, and Aditi is asking something about the registration courses. To reiterate, the TAs that conduct the practice sessions, we don't have any information about the exam questions, nor do we have information about these things. So there is a separate set of TAs, as I mentioned in every lecture. You have to contact them or directly the professor or the team that handles that part for these questions. Okay, it's 7:50. Let us start. The last sentence essentially gives it away that you're working with a ratio of population variances. Okay, so this is the scenario of comparing sample variances. So what information do we have? It says that you have a confidence of 92%. So if we note that down, confidence of 92%, you could either go into the confidence interval side or you can do the critical value or the p-value side. That I find that easier. So we can convert the confidence into an alpha. We just say 1 minus confidence is our alpha. Okay. Now, whenever you do these comparing these variances for using the F distribution, it is always recommended that you take the distribution with the higher variance as the first distribution. In this case, like N1 is 6.4, it has less than N2, which is 8.1. So it is preferred that you actually switch the order between the two. In fact, maybe we can just remove the 1 and 2 from them to avoid any confusion. All right, so we can ourselves set that our S1 and our S2 are 8.1 and 6.4. So what happens when you do this? Essentially, when you say that your S1 is the greater variance, you can always take the right side of your F statistic to compute your metrics. You don't have to worry about the lower tail one. You can always use the upper tail one. It just reduces the chances of errors. So given this, we can also say that our sample sizes are 8.1 has 15 and 18. So 15 and 18, we have our sample sizes. Now we would like to compute the F statistic. That is equal to S1 squared divided by S2 squared. Our degrees of freedom for both of them are degree of freedom for one will be N1 minus 1. Our degree of freedom, we can just write D. Degree of freedom 2 for N2 is N2 minus 1. And then we can compute the critical value. We can say that it is stats dot F distribution. I would like the PPF at 1 minus the alpha on the, which is the your upper tail. You pass in your 2 degrees of freedom, this returns the f critical value. And again, we can reuse this part, that is our decision. You can delete this part, we can write that our f statistic is this much. We can say that our critical value is this much. And our alpha, in this case, we can reduce it to 2 points. Okay, so we understand that we fail to reject the null hypothesis, meaning that the two devices that are calculating the blood pressure, there is not significant difference between their variance that we would prefer one device over another device. Now, there is another way to compute this decision to calculate as to conduct this hypothesis test, which would be to do a use a confidence interval. Now, I don't like to use this because there is a chance of a mistake here, but still, for the sake of completeness, how would you do that? Now, when you use confidence intervals, you have to use it on either side. So you have an upper tail and you have a lower tail. So you split your alpha into two parts. So alpha lower becomes alpha by 2, and alpha upper or higher becomes 1 minus alpha lower. So these are your two alphas. Now you have to compute two F criticals. So you repeat this particular part on two sides. So you will have an F critical lower and you will have an F critical upper. And in this case, you will pass lower. And in this case, you will pass higher, higher. So we have these two things. Now comes the tricky part. Now you have to compute those decision boundaries. I mean, the confidence intervals boundaries. So you will write that Ci lower is equal to something and I always end up writing higher, is something. So you would remember that when we used to compute these confidence intervals in our means rather than variances, we would do something like this. That is, we have our z statistics, we multiply it by the z critical value. Z stat by z critical. And if we are computing the Ci higher, you would do z statistic higher multiplied by z critical higher. Okay, this would be the natural order. But the order here is reversed. To compute the Ci lower, you actually have to first, rather than multiplying, you have to divide, and you have to divide by the opposite side. That is, to compute the lower critical, I mean, confidence interval, you have to use the higher critical value. And similarly, to compute this side, you have to use the lower value. So this actually happens because if you expand that probability term of this thing, this f statistics, like s1 square by this, there is another term in the denominator there, which would be sigma 2 squared divided by sigma 1 squared. So because this is in the denominator, when you essentially switch these things, this f critical goes in, cross multiplies and goes into the denominator and also switches these sides. So that's why it's more error prone. And I mean, if you have the choice, it's safer to use a p-value approach or a critical value approach rather than a confidence interval because of this swap that you have to do. So anyway, if we have these things, we can once again say that how do you make a decision? We in fact just note here that notice that the order of denominators is reversed. So how do you make a decision? In this case, when you have these confidence interval, you decide based on the value of unity. You can say that I will fail to reject this the null hypothesis if my unity, that is 1, lies between the Ci values. Otherwise, I will reject. This gives me the decision. Then once again, we can print that confidence level 100% confidence interval for the ratio of variances was this much. We'll have CI lower here. We will have CI upper here, CI higher here. And then we can print the decision to be whatever decision we get. We not have confidence level or just confidence. Okay, so the result is the same thing. That is, you fail to reject the null hypothesis, but it is just more error prone when you do it like this. Okay, so you should prefer this particular method when you're computing variances. So we can mark this particular question that this is for comparing the sample variances. How can we contact the NPTEL team? I think their course page should have a helpline website, right? You can, in general, I think, mail the NPTEL team. You can mention that I'm doing this particular course. This is my course code or something, even with just the title, and the professor should do, and they should be able to connect you with them. In any case, I hope this is helpful. Now we can go to the next question. Mhm. Have we covered? We've covered this. We've covered this. Let's do this one. Okay. So the question says, two machining techniques are being evaluated to determine how they affect the mean surface roughness of a manufactured metal component. Technique 1 is currently used in production. Technique 2 is a viable alternative. Technique 2 reduces the operating cost, so it should be adopted, provided it does not change the mean surface roughness. Okay, so you have two machines, they are both used for sort of chiseling a particular material. Technique 2 is cheap compared to technique 1, but you have to ensure that it does not that it essentially achieves the same performance as technique 1. A study is conducted in the production facility and the results are shown below, these particular results. Is there any difference between the mean surface roughness values using an alpha of 0.05? Can you comment on this situation? You have these two samples. I can provide you the data, and suppose in the second part, you can say, suppose I did not give you this raw data and rather I just give you these descriptive statistics. That is, your sample mean was this much and this much, and your sample standard deviation was this much and this much. Could you comment using just these rather than having the raw data? So again, if you can do it using a library, you can do that. And afterwards, you can write manually. The important part is to identify which test to do, which scenario does this fall into. Let me give you the data. I already go through the complete website area, but I don't know how to contact them. I think this should help, this particular thing. Swayam support. Maybe you can contact through this. And I think if you just go to the NPTEL website, it says support at the rate NPTEL. This is another thing. They also have phone numbers if you want to call them. 83. I believe one student also created a WhatsApp group for you students, like an unofficial group. So if that student is here, maybe he can share the link with the rest of you as well, if you want to join. By the way, you can assume that the two populations have the same variance. not the samples, the population. Okay, it's 8:10. We can start. The first and foremost thing is, what are we working with? What is the scenario? We notice that there are two different samples. They are independent samples, and we are interested in the difference of means. Okay, so we have independence, independent samples, difference of means. The population standard deviations are unknown, but we can assume that they are equal. So what do we use? We can use a paired independent two sample t-test, which is essentially SciPy t-test indicated this. Where is it? SciPy stats. This thing. Calculate the t-test for the means of two independent sample scores. So you can do it whether the variance is known or unknown because it gives you an option. Assume equal variance or not. So let's use this function as is. We can say that our we can write here that is our alpha is 0.05. We can say that our t statistic and our p-value are given by stats dot t-test ind. What does it take? The first thing is your sample 1. The second thing is your sample 2. You can cross check here a and b array. Then the NaN policy, we don't have to worry about this. This is when you work with pandas and if you have NaN values. The alternative is, are you working with a two-sided test or a single-sided test? In our case, we say that they should essentially be equal, not less, not greater. So our alternative is two-sided. That's another thing. Then it says keep dimension, etc., etc. Where's it? Equal variance. Where did that go? Wait, I think we shift t-test ind. Yeah, equal variance, we have to pass true. Okay, so let's see what we get. We can reuse this part. Okay, this is a z-score. We want a t-score. All right, so what do we have? Our t statistic is this much. Our p-value, we can use maybe this 0.03 compared to 0.05. So we can reject the null hypothesis. That is, they are not the same. The When you chisel using technique 2, the average, uh, whatever value it is changing. So this was when you had the full raw data, you were able to use this particular function. You provided the full sample, sample 1 and sample 2. But what if I did not give you the raw data? I only gave you the sample means and the sample standard deviations. What would you do in that situation? There is another function which is scipystats test. I think it's called test ind from stats. Yep, this one. T-test for means of two independent samples from descriptive statistics when you don't have the full data. So what do you provide? You have to provide mean one, STD1. Notice that this STD is not just, I mean, you take your sample and pass the STD. It is the corrected STD. That is, you have to pass this thing, your degree of freedom to that. That is, it is the sample standard deviation. And the number of observations, we have all three things. Similarly for mean two, standard deviation two, and are you assuming they have an equal variance? And again, the alternative, is it a two-sided test or a one-sided test? So we have all these values, we can just pass them. We can say our t, can write here approach 1, full access to data. Approach 2, limited access to uh, descriptive stats. In this case, we can say that our t statistic and p value are given by stats dot t test underscore this, and it takes three things. It takes mean one, which is equal to, we should first write these, x1 bar, x2 bar is sample one dot mean, sample two dot mean. I mean, we can just pick these values here, but still we can just recompute them as well. So we can say it is 4.601. This is 4.695. Similarly, we have S1 and S2. S1 is 0.083 and 0.076, 0.076. We have this. So mean one is x1 bar, STD1. Notice that STD1, if you had to compute it, you would do something like this. S1 would be sample one dot STD along with the degree of freedom. So these two values are not the same. If you just print these, notice these are not the same, 0.077 and 0.082. So this would, you do this one when you have to compute the population standard deviation. This is when you have to compute a sample standard deviation. Okay, so anyway, we have STD1, it is already corrected. This is S1, and we have number of objects. That is how many values are there for sample one. It is n1 comma n2. It is equal to, I think they're identical, 8 8 in both cases. So we can say 8 comma 8, 1 to 8, yes, 8 8, and we can just pass n1. Then we do the same thing a second time. We have mean 2 is x2 bar, standard deviation 2 is s2. This is n2, and we assume that they have an equal variance. We assume that not assume, we know that we want to compute the two-sided test, and the rest is identical. We can just print this part. Okay, same results, 2.36, slight change because these values we have limited them to 3 decimal places. But if you were to compute the exact mean, uh, you have a bigger number, like you have more decimal places. So because we are rounding off, it affects the t statistics slightly. So this is another way to do it. Now that you know how to do it using these libraries, can you do it manually? Can you try to do this thing manually? You know what to do. Independent samples, difference of means, population standard deviations are unknown, but you can assume that they are equal. Can you do this? You can refer to your lectures again. This should be in lecture 20, I believe, or 21, one of the two. All right. So let's start with the manual calculation. We have our two samples. We can calculate their means. We have x1 bar and x2 bar. They are sample one dot mean and sample two dot mean. We already have S1 and S2. We can also recompute them. That is sample one dot std. This is a sample standard deviation, so we have to pass this thing sample two dot std, and again this is equal to this. Now our sample sizes are n1 and n2. They are length of sample one and length of sample two. These are our briefly the three things that we have. Now we have to pool these standard deviations, and after that, we can calculate the standard error. So to pool the standard deviations, we have this formula where you do n1 minus 1, which is essentially your weighted average. You have n1 minus 1, which is your degree of freedom for the first sample. You multiply it with the sample standard deviation square. So this is your first term. Okay. The second term is n2 minus 1 times the standard deviation, sample standard deviation of the second one. You have this, so this becomes your numerator. This you have to divide by the sum of your weights, which is essentially n1 minus 1 plus n2 minus 1, which essentially becomes n1 plus n2 minus 2. Okay, and the whole thing, you just take it as a square root. np dot sqrt, or you could just enclose all of this into this and say 0.5. This is your uh, pooled standard deviation. It's just a weighted average of the two. Once we have this, we can calculate the standard error. It is simply your standard, your pooled standard deviation times the square root of, I mean, essentially, it's actually, you can take SP inside. You can write like this, like SP squared divided by n1 plus SP squared divided by n2, and then you can take the root, but essentially you can take this part out common. So you can just write SP multiplied by, this would just be 1 by n1 and 1 by n2. Okay, so for brevity, we can maybe put them in close. So SP times this. So also note that when you take the power, it has the highest priority. So you don't have to add additional braces here. If you want, you can for your own convenience, but it's okay to have it like this as well. So we have this SP times 1 over n1, 1 over n2, and we have taken the square root. Now, what's the delta? Based on the null hypothesis, we assume that there is actually no difference between the two means. So we can assume that the delta is 0. So how do you compute your t statistic? Your t statistic is simply is equal to x2 bar minus x1 bar minus delta, which is again 0, divided by your standard error, as you always do. When you use a t distribution, you always need the degree of freedom. So your degree of freedom will be n1 plus n2 minus 2. Again, this happens because you have n1 minus 1 plus n2 minus 1. So that becomes n1 plus n2 plus this thing. So this is your degree of freedom. And then you can calculate your p-value. You can have your alpha to be 0.05, our p-value, because this is a two-sided test. Again, this is twice of, we can take the higher tail side. So we can say stats dot t dot cdf. Let me take the absolute value of the t statistic. And you pass the degree of freedom. This should be enough. And the rest of it we can reuse. Okay, so this is the statistic on the lower tail side. We have calculated it on the higher tail side, doesn't matter. So 2.361, the p-value is the same, 0.03, and we reject the null hypothesis based on this. So we have done it using three ways. So coming to the last part, we can go over ANOVA. Okay, so a sports scientist wants to compare the effectiveness of three different training regimes in improving the vertical jump of its players. The three programs are so and so, program A, B, C, which are so and so, so and so, so and so. After 8 weeks of training, a random sample of athletes from each group is tested. The improvement in vertical jump height is recorded below. That is, these five athletes produce this much jump. Program A, this was this, program B, program C. Is there enough evidence of a difference in the mean improvement among the three training programs? So, can you say that the program regime that the player went through has affected their jump, or is it mainly the variability within the group? That is, ANOVA essentially tests that. Is the variance coming because your own group is a lot varied, or is there enough variance between the groups? So you can do that, and you don't have to do it obviously manually. You, I would like you to use this function. Use, oops, use this function to calculate ANOVA using this thing. And if you find out that ANOVA says that yes, there is enough evidence to believe that these three are not identical, that there is some difference between the groups, can you conduct a post hoc turkey test to identify which of the programs has the most difference? And for that, again, you can use another function called pairwise turkey SSD. You will get it from this. It's a different library, this thing. So see if you can do that. Let me paste the data for your convenience. So go to these pages, SciPy starts F1 way, and similarly this one. You can read the documentation. That is, what are the required arguments? Do I need to create them? Do I already have them? And pass them accordingly. I'm not speaking. That's why. All right, we can start. Our alpha was 0.05, and we want to compute the ANOVA value for this thing. So for ANOVA, it returns the F statistic and a p-value. If we notice here, the one-way ANOVA tests the null hypothesis that two or more groups have the same population mean, and it returns the statistic, which is the F statistic, and the p-value, which is a float. So what does it take? We can use stats.f one way. We have to pass the three essentially columns, three data points. We have df.a. You can also pass this like this dfa, but this is just cumbersome. So dfa, dfb, dfc, and this essentially gives us the whole thing. Then we can just print them out. That is, our f statistic is this much. Our p-value is this much. And as usual, we can take the decision part as usual. Okay, so our F statistic is this much, our p-value is this much. We can remove this one. We already have it. And at alpha equal to 0.05, we can reject the null hypothesis, which means that there is sufficient variance between the groups compared to within the groups. Now, how can we know which particular treatment has the highest effect on the vertical jump? So to do that, we can go for the turkey test. Now, this is where the main part is. This is quite easy. This part is a bit tricky. So we have the turkey test. What do you do for the turkey test? If we go here, so the turkey test requires a response variable and the group. So it does not quite mention how it requires them, but a key part is that you have to melt your data frame. Now, what does that mean? So if you call df dot melt and you pass this thing, let me show what happens, and then we can discuss it. So what melt does is that is, for example, you have a particular row, row zero. Row zero has three columns, A, B, and C, and you have these values. Rather than having these in a single row, you want one value per column. So 0A becomes one column, 0B becomes one column, 0C becomes another column. So that is what happens here. You say that I would like to create a new column which will be named program. That column will essentially hold the initial column names A, B, and C. So your 0A comes here, 0B comes here, 0C comes here. Okay. And then these values 4.8, 6.1, 5.4, they are captured by this thing. That is, I want to name the new thing improvement. Okay. So that is what your melt essentially does. It breaks down this data frame to have a single column, and it essentially hashes these columns into a single column, that is ABC, ABC, ABC for individual columns. So you would notice that here you had 4, 4, 3 is 12. So now you have these essentially these columns. In this case, now this improvement column is your this endogenous value, that is the dependent value, and your groups are this particular thing, your program A, B, 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 C, C, C. You cannot pass this thing to the turkey test. So now we can maybe save this here. That is, we create a new data frame df using this melting of our data set. Following that, we can do turkey is equal to pairwise underscore. Wait, we haven't imported it. Okay, so our endogenous variable is df dot improvement. Our groups are given by df dot program, and our alpha is 0.05, or we can just pass alpha. I think we defined it earlier. Yes, we defined it earlier. And following that, we can just print this. Okay, so these are our values. So the key thing to note here is this particular column, which is mean difference. The mean difference gives you the difference of 2 minus 1. So we can write this here. Mean diff is mean of group 2 minus mean of group 1. So based on these, we can see that B has a higher impact on the vertical jump compared to A. Okay, so we can note that down. B is greater than A. C has a greater impact than A. Okay, so A is essentially discarded. So the main tie is between B and C. C has a lower impact compared to B because the difference is negative. So we can conclude that B, program B, has the highest effect on the vertical jump. Okay, so that is essentially our ANOVA test. I would like to give you a homework assignment of computing the ANOVA manually. When I upload the notebook to the GitHub, I will include this part, but I would like you to try it yourself. That is, can you calculate this ANOVA thing, this F-stat and decision value yourselves following the lectures. Okay. To conclude, you will find the uh, notebook uploaded here. Let me paste it here. You will find the recorded lecture that we are just having at this playlist. The fifth video will be up in a couple of hours. So if we don't have any questions, we can end the meeting. All right. See you all next week.